Hello. For this example, we will calculate how fast the pole vault jumper has to run to get over the pole onto the safety mat. For this example, we will use the kinetic energy of the pole vault jumper. The kinetic energy of the pole vault jumper is equal to a half times his mass times his velocity. All of his kinetic energy is transferred when he reaches his highest point to potential energy. And the height of the pole is at height h. So therefore, the potential energy of the pole vault jumper is m times g times h. Because of all the transfer of this energy, we can say that the kinetic energy is equal to the potential energy, which will result in a half m square v squared times m times g times h. Because there's m at both of these formulas, it will fall away, and we will get, if we rearrange the rest of the formula, we will get v is equal to the square of 2 times g times h. This is the equation on how fast the pole vault jumper has to go, depending on the height of the pole. For the smarty pants that have noticed that this equation isn't used in the real world, because we say with this equation that all the kinetic energy is transferred to potential energy, which will say that at the top of its movement, the pole vault jumper is completely still, and therefore, if the wind blows the wrong way, he will fall back on where he jumped at the first time, and therefore doesn't hit the safety mat, which is very dangerous. For our second question, there's also energy stored in the pole because of its curvature. We can also say we can see that as a spring. This will have the length L, and at this point, the effective length of the pole is shorter than the large L, because this is the total length of L. We can also visualize it a bit better by this is equal L, and this as the length of L. This spring is more like this, and this spring is still a bit shorter. So therefore, this difference can be seen as the compression, as the total compression. So if we write it in a formula form, and as we have seen in the previous exercise, there's still some kinetic energy which is used to come more to the pole or over the pole. So therefore, we don't have to forget that one, because we have seen in the previous exercise that we shouldn't forget the velocity of the pole vault jumper while the pole is compressed. We can write it as the kinetic energy at the beginning, which we call 1, is equal to the kinetic energy at the point of L, small l, plus the potential energy, because he also goes to the height. He also has a certain height, which we can write as, if we take this one for example, we can write this as height 2. So the potential energy at this point plus the energy of the spring. We can write this formula as follows: a half times the mass of the jumper, which doesn't change. So therefore, the only change in those two kinetic energies is the velocity. So therefore, we can write velocity 1 squared, which is equal to a half mv velocity of situation 2 squared plus m times g times h2, which is again this height, plus a half times k. The k is for the spring constant of the pole, and u is the deformation, which is also squared. Now we have to make the formula such that we can calculate the deformation at a certain v2 that we know and a certain height. Yeah, so we can write this as a half k times u squared, which is equal to a half m v2 squared minus v1 squared plus m times g times h2. Now to make it good, u squared is equal to m v2 squared minus v1 squared plus 2m times g times h2. Now u is equal to m v2 squared minus v1 squared plus 2m times h times g times h2 divided by k and a square root of that. And for the ones that pay attention, I forgot here the k. Now we have the deformation of the pole at a certain height and a certain velocity, and that's how we calculate the total deformation. Good luck.